Hello all, welcome to this course on time series modeling and forecasting using R. So this is the last week that we are entering into, and then as seen in the last couple of sessions this week, the broader topic for the entire week was machine learning aspects, or rather machine learning integration into time series applications. And again, the first two sessions were more from an introductory perspective, where we sort of saw the different ideas about how and exactly what are the different ML techniques that one can adopt, and how do you sort of integrate each and every one into some sort of an application pertaining to time series data. The very first session, we sort of discussed a lot of different ML techniques, and then again, if you're not very confident about any of them, then maybe one has to really pick some elementary book on ML and then try to read further, because this course is not meant for sort of developing the details of each and every ML technique. All right, so the last week I've kept specifically for just to make you all understand the integration of ML techniques and then time series applications per se. Okay? And again, if you remember, just to give a very short recap, in the very last session we talked about particularly three different kinds of ML techniques, where we talked about, let's say, starting with linear regression, then we talked about random forests, and then support vector machines, etc. Okay. Now, in this session, we'll talk about a few other ML models, and then we'll see what to do next. Okay? And then, like I said, even before, the session afterwards would be entirely based on neural networks ideas and then integration of neural networks into time series. But again, coming back to this session, we'll focus entirely on some other advanced ML models. Let's say if you're moving from a linear regression setup to maybe a classification sort of a setup, or let's say random forest, decision trees, SVM, clustering, right? Or let's say k nearest neighbors. So we'll talk briefly about all these different ideas along with their advantages, limitations, and a few examples, just to make sure that all of you understand the idea about how exactly can one sort of integrate the thought process behind, let's say, a particular ML model and then a time series application per se. Okay. So as you see in front of you, the heading of this slide is few other ML models. And again, we'll start with the very famous sort of an ML model called as k nearest neighbors, or in short KNN. Now again, I'm sure that many of you, if you have some knowledge about ML, then you must have come across this KNN technique. So let me write it down. So in short, it's called as KNN, or rather k nearest neighbors. Now again, here the idea is that, let's say, if you have a set of inputs, and then the idea is to sort of find the nearest neighbors pertaining to the target variable, right? And then sort of create a cluster around that, and then try to estimate the parameters and then eventually forecast. Okay. So again, this slide is just an introduction about KNN. So the k nearest neighbors, or in short KNN, is rather a versatile machine learning algorithm that can be adapted for time series forecasting or classification. Okay. Now again, if you remember, just to again give you a short brief recap, that let's say if you pick any ML technique that can has its use cases pertaining to both sort of a regression kind of a problem or classification, right? So regression means that the dependent variable yt need not only be a categorical variable, it can be a numerical variable also. But when it comes to classification, necessarily yt has to be a categorical variable, and then eventually the classification algorithm that one has under this umbrella of ML, it sort of classifies all the different input variables into different categories. Okay, so based on a set of input variables, it categorizes each one of them into different categories, and accordingly it gives the output. So again, on one hand, we have a regression kind of a problem. Again, this is just a small recap before we begin with anything new. And on the other hand, let's say if yt is binary or let's say categorical, then the class of problems is called as classification sort of problems. Okay. So in short, the KNN is a versatile ML algorithm which can be adapted for time series forecasting or classification. In time series tasks, KNN is primarily used to identify the most similar historical patterns, which are also called as neighbors, and use their outcomes to predict the future values. Okay? So as discussed a very short while back, that the primary idea behind KNN is to identify a set of most similar historical patterns, and these similar historical patterns are called as neighbors. The other terminology is neighbors, and use their outcomes to predict any of the future values. So essentially what it does is it sort of finds the k nearest neighbors. So when we say the k nearest neighbors pertaining to any single point, we have to actually find out some similar historical patterns around that single point and use their outcomes to predict the future values, and hence the name k nearest neighbors. Okay, so hopefully the idea behind KNN should be clear before we proceed with, let's say, some of the examples, their applications, and so on. All right. Okay, so what exactly are the steps in action? So let's say if one has to implement the KNN, be it along with the time series application or without a time series application, but in general, let's say if you're sitting in a time series course and we're discussing the integration of, let's say, KNN with time series application, we'll talk about steps in action accordingly. Okay. So the very first step is rather to convert any time series to a supervised problem. So what do you mean by that? So again, if you remember vaguely, in the last session we talked about an idea that any ML algorithm or the entire umbrella of ML can be categorized into two different sets of problems. The one is supervised. So again, just a short recap. And on the other hand, you have unsupervised, obviously. Okay. And let's say regression, classification, KNN, then let's say SVM, decision trees, random forest. So all these fall under supervised category. Now again, what do you mean by supervised? Supervised means that whatever inputs you have or whatever incoming data points you have are sort of labeled and you exactly know that which data point means what. Okay. And rather on the other hand, what do you mean by unsupervised? So unsupervised means that the input variables or the data points in the input set are not labeled. And one very famous example under unsupervised is clustering, or let's say k-means clustering, and so on and so forth. Okay. But here, if you want to sort of implement the KNN or k nearest neighbors, and again, of course, with an integration with a time series application, the very first step is to convert any time series to a supervised problem, which means that you should exactly know that which observation sits in which time point and what exactly it means. Okay. So essentially, you want to label each and every data point. Okay, so again, just to recap, so convert the time series to a supervised problem. And inside this, the first major point, you have two subpoints. So the first subpoint is a univariate time series is sort of converted into a supervised learning format by creating some lag features. Now again, remember one thing, that if you want to implement any ML algorithm, there has to be a set of input variables, which are again called as features. Okay, so the technical term in ML terminology is called as features. And again, you should remember that in the first and second sessions this week, we talked about an idea called as feature engineering, right? So the whole idea about feature engineering is to pick the correct features and then adjust the features and then sort of control each and every feature so as to sort of implement them into the ML model. Okay? So again, just to recap, a univariate time series is converted into a supervised learning format. So supervised is important here by creating some lagged features. For example, let's say the idea is to predict YT. So YT is what is the response for us. So essentially the idea or the goal is to predict YT. You can use the features which are its own lagged values. Okay, so let's say YT minus 1, YT minus 2 up to YT minus P, where P stands for the number of lags. And again, as seen even in the last session or the one before that, this is a very standard technique that one does, right? So the integration of ML and time series. So since you already have this set with you, right? So let's say if you want to predict the current state YT, you obviously have its own historical data points, right? So YT minus 1, YT minus 2, YT minus 3, etc. So why not make use of them in sort of getting and trying to sort of assuming that they are features, basically. Okay. So this is the first step. Then the second step is similarity measure. So what do you mean by that? So similarity measure means that, again, remember what the broad idea about KNN is. So again, probably I'll illustrate very briefly. Let's say you want to predict at this point. So essentially the goal is to find the k nearest neighbor. So let's say you have all these observations, right? And you want to find a small subgroup such that it's sort of neighboring this target variable. So probably this, right? So any data point which falls inside that circle could be considered as a k nearest neighbor for that bigger red dot. Okay. So hence, so how do you sort of formally measure the distance of all these observations from the target variable? There has to be some yardstick, isn't it? And this yardstick is called as a similarity measure. So the similarity between time series segments is calculated typically using some distance measure. So let's say Euclidean distance or something like that. So again, just to give you an example here, so what we'll essentially do is to find out the Euclidean distance between each and every observation with the target variable. And essentially, whichever Euclidean distance is minimum, we'll consider those observations in the k nearest neighbor set. So hopefully this idea is clear. So obviously these points here, since being far away from the target variable, won't make it into the KNN set here. Okay, and essentially this whole exercise is called as similarity measure. So one requires some sort of a similarity measure to sort of capture the minimum distances between all the observations and the target variable. So again, just to recap, so the similarity between time series segments is calculated typically using some Euclidean distance. And second step inside the similarity measure heading is that each time step, or rather row, is treated as a vector in a p-dimensional space. Okay, so again, each time step or row is treated as a vector in a p-dimensional space. Now again, why p-dimensional? Because again, if you go back a slide, then essentially what you're taking as features is nothing but the last p lagged values. Okay, so if you're taking the last p lagged values, and then let's say if you have observations for each one of them, then the entire set would be in p dimensions essentially. Okay, so hopefully the first two steps are clear, that one should always convert a time series to a supervised problem, and then the second step is one should always invoke some sort of a similarity measure to measure the Euclidean distances between all the time series segments along with the target variable, and whichever distance measures are minimum, you keep them in the k nearest neighbor set. And then the third step is prediction. So once you're through with, let's say, estimation, finding the k nearest neighbors, then estimation, then the last step is prediction. So for any given test point, so test point is any given point or rather a target variable for which you want to predict in the future. Okay, so for any given test point, the algorithm finds the k nearest neighbors from the training set. Now let me pause here for a second, and in the first two sessions I did not discuss a very important idea, is that if you're implementing any ML technique, there is always this idea about splitting the data set into a training set and a testing set. Now again, I'm very sure that most of you must already know this. If you have some awareness about, let's say, machine learning, or all the ML techniques in general, but the primary idea is that we should split the data set into a training set and a testing set. And again, why should we do this? So we should fit the ML model, or we should rather run the ML model on the training set. And here we sort of assume that the training set is slightly larger. So one can split the data set into 80%, 20%, 70%, 30% in this ratio. So that training set is slightly larger. You run the ML model on the training set, and then you try to predict on the testing set, so that you can find out the accuracies. Okay. So let's say you reserve some part of the data set for measuring the accuracy of that particular ML model. So let's say you build, for example, let's say regression or classification, SVM, any ML model, or let's say KNN. Then you run the model on the training set, right? And then predict that. And then you sort of compare those predictions with the actual data set in the testing set. And from the testing set, you get the testing set accuracy. Okay? So hopefully this small exercise is clear, that once you split the data set into training part and the testing part, you run the ML model on the training part, then you sort of predict in the future, and then you sort of compare the predictions along with the testing set, and then find the accuracies by, let's say, taking any standard measures, let's say MSE or root mean square error and so on. Okay. So again, coming back to prediction for a given test point. So test point means what? So any point in the testing set. Okay, this is not. So for that point, we haven't trained the ML model yet, right? So we only train the ML model on the training set, and then we sort of compare the predictions on the testing set. Okay. So for any given test point, the algorithm finds the k nearest neighbors from the training set. So let's say from the training set, you run the KNN technique, and then you sort of find broadly the k nearest neighbors, and then you have a single point in the test set or the testing set, and you use the ML algorithm which is being fitted on the training set to find out the k nearest neighbors of the test point. So hopefully this is clear. All right. Then the second point is that the output for the test point is computed as, let's say, the average for regression problems, or the majority class for classification problems. So essentially what would be the final output? So the output for that particular test point in the testing set is computed as either the average if the problem is from a regression context, or there's an idea called as majority class. So majority class is whichever category is weighed the most as per the ML output. Okay. So if you have a regression problem, then one can take the average. If you have a classification problem, then of course one cannot take the average, because YT is categorical, as discussed a short while back. So there we have a concept called as a majority class. Okay. So the prediction contains these two subpoints. So you pinpoint a test point in the testing set, then you run the algorithm on the training set, find the k nearest neighbors pertaining to the test point corresponding to the training set. And how do you get the output of the test point? So the output of the test point is computed as simply taking the average for regression problems or by figuring out the majority class for classification problems. Now, what exactly are some of the key components when it comes to KNN? So again, many of the key components would be similar to, let's say, some of the ideas we discussed in the last session pertaining to regression or SVM, random forests, etc. For example, feature engineering. So again, feature engineering is important here. So let's say lag features represent past values as predictors for future values. So generally speaking, one actually takes some lagged values of yt itself, let's say yt minus 1, yt minus 2, yt minus 3, etc. as predictors for its own future values. Second point is optionally include some rolling statistics. So again, if you vaguely remember from the last session, we discussed the idea of rolling statistics. And then one very famous rolling statistic is a moving average, right? So optionally, one can include some moving averages or rolling statistics to capture the trends. So one can actually include both these ideas as features. Okay? And then this entire exercise about identifying the features and controlling the features and then running the ML model is called as feature engineering. Okay? Then the second key component when it comes to running a KNN is hyperparameters, right? So what exactly are the hyperparameters under KNN? So the very first hyperparameter is obviously k, right? Now again, k is a number, right? So k can be, let's say, 10, 15, 20. So if k is 10, what do you mean by that? So you're looking at the 10 nearest neighbors. Or whenever k is 15, you're talking about taking the 15 nearest neighbors. Or if k is 20, then you're talking about taking the 20 nearest neighbors to the test point and so on. So identifying or rather controlling the value of k is rather important, right? I mean, you should not go too overboard with the value of k, and k should not be even too minimum. Okay. Now remember, one very important idea when it comes to ML technique is that you have an idea about underfitting and overfitting. So again, one should not go too overboard and one should not be underboard as well. So one should try to balance all the essential aspects. So for example, identifying k or finding out k, one has to strike the balance somewhere. So again, what do you mean by k? So k is nothing but the number of neighbors to consider. So should you have 10 nearest neighbors or 12 nearest neighbors, 20 nearest neighbors, 30 nearest neighbors, etc. And the second important hyperparameter is the distance metric. So typically Euclidean distance, but you do have some other alternative distance measures, let's say Manhattan distance and so on and so forth. Okay. So one has to control for these two hyperparameters. So the first one is k, which stands for the number of neighbors to consider. Second one is a distance metric, typically a Euclidean distance, or its own alternatives like Manhattan distance, etc. Okay. The third key component is normalization. So time series data often needs to be normalized. So what do you mean by normalized? Normalized means scaled down to ensure that all the features contribute equally to the distance calculation. So one should actually go ahead and then do the normalization by scaling them. Okay, so each feature should be scaled down or normalized. And then fourth one is model evaluation. So again, you have a standard technique of model evaluations. One can use common metrics for regression, let's say MSE or MAE, etc. And if you have a classification problem, one can use, let's say, accuracy, precision, recall, etc. Okay. Now, what are the advantages of KNN? So simplicity, so easy to implement and interpret. Non-parametric. So non-parametric is an important advantage of KNN. So non-parametric means that no assumptions about the underlying data distribution. So one need not assume that distribution is normal or exponential, something like that. Okay. And handles non-linearity pretty well. So can capture non-linear patterns in the data. So again, all these ideas now are one step ahead of the linear regression. So linear regression cannot handle non-linearity, obviously. And all the other advanced ML techniques, you're slowly moving from linearity towards non-linearity. Okay. So simplicity being a non-parametric approach and handling non-linearity are some of the advantages of k nearest neighbors technique. On the other hand, what could be the limitations of KNN? So obviously it's costly, so computationally costly, so high for large data sets, as all the distances need to be computed for each prediction. Okay. So if you have very huge data, then you have to compute each and every distance, let's say Euclidean distance, Manhattan distance, whatever, but you have to compute all the distances, which is quite a large task. And then second point is curse of dimensionality. So what do you mean by that? So high dimensional data can dilute the effectiveness of distance metrics. Hence, one should carefully select the number of lag features and normalize the data. So choosing carefully the number of lag features and normalizing the data set are some solutions towards controlling the curse of dimensionality. Thirdly, no explicit model. So KNN is memory based and doesn't create a model, making it less efficient for frequent prediction. So KNN, one cannot see the model, of course, being a black box technique. So one cannot really control the model per se. Okay, so no explicit model is there inside the KNN. Okay, so one simple example regarding KNN, and then this is a very famous example and pretty much used effectively by a lot of people, called as pattern recognition, right? So what do you mean by pattern recognition? And then what essentially is the integration of pattern recognition with time series? So particularly pattern recognition in time series involves identifying segments of a time series which match a given pattern. So let's say if you have a pattern in mind or in front of you, and then you want to find out some segments from the time series data set which match the given pattern that you have or belong to a specific predefined category. Okay. So some examples could be, this could include identifying, let's say, recurring events, anomaly detection, or grouping similar subsequences, etc. So the whole idea about pattern recognition is, let's say, if you have some pattern, right? So let's say I'll give you a hypothetical example. Let's say you have this pattern in mind, okay? And let's say if you have some time series which is running like this, and I'll give you an example, let's say something like that, and probably somewhere in between you see that you can sort of spot the same pattern probably here, right? The one which is given here. So this exercise is called as pattern recognition. So the idea is that you split the time series into multiple subgroups and then run the KNN, identify the k nearest neighbors in some way, and then try to identify that which subgroup or which category of this entire time series is sort of similar to the pattern in mind. Alright? And the examples here are, let's say, identifying recurring events, anomaly detection, or grouping similar subsequences, etc. For example, we can use the KNN to recognize specific patterns in stock price movement. So similarly, exactly to what we talked about in this example, that let's say if you want to identify some recurring patterns in the behavior of a stock, right? Then one can use KNN, or let's say machine vibration data, or EEG signals to detect anomalies or classify patterns, etc. So how do you do this? So a set of brief steps. So the first step is define a reference pattern. So there always has to be some reference pattern. And again, if you go back a slide, then the reference pattern in our case was something like that, which I drew, right? So this would be the reference pattern. And then you try to identify or simulate a specific pattern you want to detect. Let's say example, a sinusoidal wave or a spike or a flat trend, etc. Okay. So there has to be some reference pattern, and then you sort of browse the entire time series observations or the data points, and then try to find out that whichever segment of the time series sort of resembles the reference pattern. Okay. And then segment the time series. Second step is segment the time series, of course. So divide the series into overlapping or non-overlapping windows, which are also called as subsequences, which capture the local patterns. Okay. So again, just to give you an example, let's say if you have this overall time series which runs like this, and let's say for some reason the time series behaves like that. Now what we'll do is we'll divide this time series into, it could be overlapping segments or non-overlapping segments. So let's say you have non-overlapping segments, probably something like this. Okay, so let's say you divide the time series into 1, 2, 3, 4. So let's say 4 segments. And then you sort of run the reference pattern, you have the reference pattern in mind, and then you see that which segment is sort of looking or rather captures the reference pattern very well. So in this example, you can see that the third segment here sort of resembles the reference pattern that we have. Okay. So once you segment the time series, then you sort of capture the reference pattern, you bring the reference pattern and then see that whichever segment sort of resembles the reference pattern. Okay. Then extract the features. So of course it's a KNN, you require some features. So again, for each segment, you compute the features. So features could be what? Let's say mean, variance, slopes, Fourier coefficient. So they represent the subsequences. So there has to be some model. So even if the model cannot be written down using pen and paper, but then you require some input variables, which are called as features. Then the next step is train the KNN. So KNN is an ML technique. You want to train the ML model on the training set. So use the labeled data where segments are classified as pattern found or no pattern. So you sort of run the entire KNN exercise or KNN model, and then whenever it sort of resembles the reference pattern, then it sort of triggers this idea that pattern found, or if it's not able to find out the reference pattern, then it triggers this idea which is no pattern. Okay. And then lastly, test on unseen data. So again, as discussed a short while back, that once you divide the data into training set and testing set, you want to implement it exactly on the test set. So apply the KNN to classify new subsequences as matching the pattern or not. Okay. So briefly, these are the steps, all right, when it comes to KNN for pattern recognition. Now, what exactly are some of the other applications? Let's say identify abnormal patterns in machine sensor data, let's say such as vibration or temperature fluctuations. Detect head and shoulders or cup and handle patterns in stock prices. Recognize specific patterns in ECG signals, such as arrhythmias. Or detect rainfall patterns in weather time series. So, all these are some other applications when it comes to pattern recognition. And in each one of these applications, one can again implement KNN very easily. Now again, this is a slightly different idea which is called naive Bayes. So naive Bayes is a classification problem. So naive Bayes for time series. So we'll discuss very briefly as to what you mean by naive Bayes. So naive Bayes is a very simple probabilistic classification algorithm. So one should understand this, that it's not a regression problem, it's a classification problem based on the Bayes theorem. So again, I'm very sure that you must have studied the Bayes theorem sometime back, even in school, or let's say early college days and so on and so forth. So this naive Bayes idea is sort of revolves around the Bayes theorem. It assumes that the features, let's say example lag values in time series, etc., are conditionally independent given the class label. This makes the naive Bayes computationally efficient and easy to implement even for time series tasks. Okay. So just to give an example, let's say in time series applications, naive Bayes can be used to classify, let's say sequences or subsequences of data into some predefined categories. For example, let's say identifying if a given time segment belongs to a normal or anomalous class, etc. Okay, so the whole idea about naive Bayes, so I just thought of putting this slide there just to sort of extend a step ahead from KNN. And the naive Bayes is particularly for classification problems. So one cannot bring in any regression problem inside naive Bayes. Okay? And the whole idea revolves around the Bayes theorem, as it sort of assumes that the features are conditionally independent given the class label. So the whole idea behind classification problems is to classify each and every point in the output set into different categories. Alright. So just to give you a time series application one more time is that, let's say if you want to identify if a given time segment belongs to a normal category or anomalous class, etc., then in all these applications one can implement the naive Bayes. Okay. So hopefully by this time you have some understanding about different ML techniques, the applications in time series, how do you implement each one of them in time series, and so on and so forth. Now, when we'll enter the next session, so the next session would be entirely devoted to neural networks for time series. So we'll shift from, let's say, a standard ML approach to more from a deep learning approach. So let's say neural networks, and there we'll discuss one very famous model which is called as NNAR. So we'll try to integrate the neural networks and auto regression. Okay? So all of that in the next session. Thank you.